Hello everyone, my name is Yulin Wei from University of Illinois, Urbana-Champaign. Today I'm going to present our work, Angle of Arrival, AOA Factorization in Multipath Channels. This is a joint work with my advisor, Ramesh Roy Chaudhary. Angle of arrival is the angle in which a signal arrives. Imagine a user is speaking to a smart speaker like Amazon Echo from some direction, and there are 6 microphones on Amazon Echo, and they will jointly estimate the user direction theta. With a microphone array like Amazon Echo, we can estimate the signal AOA. Here we list 3 different AOA scenarios from easy to hard. The easiest one is a single speaker directly speaking to the microphone array. In this case, we only need to estimate 1 AOA. The next level is when we have many uncorrelated sources, like there are many speakers speaking simultaneously, and we want to know the AOA of each speaker. Many existing works, like music, can solve this problem. But in most cases, the speech will create echoes. So the signals from different directions will be correlated. Like in the example here, the black echo and the direct path are highly correlated. AOA of any sources, correlated or not, is still a challenge problem, and this is the target of our work. The signal comes from any directions, may be correlated or uncorrelated, and we want to estimate the AOA of each path. But why do we need to have the AOA of the echoes? While many AOA applications require only the direct path AOA, knowing the echo AOA can enable some unique applications. One example might be the indoor localization. If we place the Amazon Echo next to a wall, from the direct path and the echo AOA, it can use the reverse triangulation to estimate the user location. Another example might be the silent zone. If a user wants to watch TV while his baby is sleeping, the TV must estimate all the echoes AOA to this baby and cancel them so that the baby will feel silent. With more information from the received signal, we expect more cool applications in the future. This presentation consists of 3 parts. Because AOA is a mature research topic, we will first introduce some AOA primer, existing works, and challenges, followed by our proposed AOA algorithm, and lastly, we will show the results. For the AOA primer, let's start from the easiest one. A single user and 1 path. When the user speaks Alexa from the top right of the array, the acoustic signal will first arrive at these 2 microphones. We mark it red, and then the green microphones, and lastly the black microphones. If we plot the received signal along the time domain, we can see a signal delay between any microphone pairs I and J, denoted as tau ij, and this delay depends on the AOA of the incoming signal. So if we can estimate this delay, we can map it back to the signal AOA. Using this toy example, we can explain how traditional AOA algorithm works. Because AOA is just a function of the delay tau, we will first compute the microphone delays for all the possible AOAs. Next, we apply these delays to the received signal. Only if we choose the correct AOA, in this case from the top right, the delayed signal will align along the time axis. But what if there are 2 passes? Here we come to the case of more than 1 speaker, but these speakers are uncorrelated. We will only give a high-level idea on how current work solve it, and why it cannot directly be generalized to any sources and echoes. In addition to the first speaker, now we have another speaker speaking OK Google. Because he is at the bottom left of the array, this signal will first arrive at the black microphone, and then the green microphone, and lastly the red. If we look into the received signal on every microphone, because the signal from 2 speakers, Alexa, OK Google, mixed together, it's hard to detect the signal delay tau ij. To solve this problem, existing works like music or aspirates analyze the received signal and finds that, well, if two signals are uncorrelated, then we can mathematically separate them. It's like the human ear can separate the violin from the piano even if they are played simultaneously, because they are very different. But if there are echoes from different angles, the signals will become strongly correlated. And the echoes are strong, and it's like listening to the violin in a concert hall. The echoes are strong, and it's hard to tell in which direction does the reflection come from. Therefore, if signal sources are correlated, like one is the echo of another, existing work cannot find the AOA of each path. So this paper targets for the multiple echo scenario. We want to know the AOA of each echo. In the rest of the presentation, we will use the example of multiple echo from one source, but this algorithm works for multiple source, multiple echoes as well. Now we have finished all the primers and the challenges. Let me explain our new AOA algorithm. The inside of our algorithm is simple. We want to cancel the known paths iteratively, one by another. Let's see a toy example of a direct path and a smaller echo. This is the received signal, and the direct path arrived at the red microphone first, and later the smaller echo arrived at the green microphone first, denoted as the dotted line. If we use the align and cancel method mentioned before, we can align and cancel the direct path. So the residual does not contain the direct path. Now we plug this residual back to the align and cancel algorithm. This time, the direct path will not pollute the echo AOA estimation. But there is a challenge here. How can we cancel these mixed echoes in the residual? A short answer is we need to align it with another residual from another microphone pair. We now take the residual to the input and get another residual from the other two microphones, and we can find the correct echo delays to align and cancel them. And therefore, we can use a residual pair to estimate the second AOA. In this paper, we propose iterative AOA or IAOA. Let's see the flow of our algorithm. For every microphone pair, we use align and cancel algorithm to find the direct path AOA theta 1. And after the direct path is cancelled, we pass the residual into the second round. And for every residual pair, we apply align and cancel again to find the AOA of the echo theta 2. Note that a residual pair consists of 4 microphone signals because each residual needs 2 microphones. And we can cancel the echoes in the second round and propagate the residuals to the third round, where we align and cancel on pairs of residual pairs, and so on. With IAOA, we can solve many echoes one after another. In the last of the algorithm part, I would like to zoom into 2 non-trivial designs in IAOA. First is how we can cancel the direct path using the channel. And second is that how can we cancel the residual using a channel bank. For the microphone I, its received signal Yi is the source signal convolved with the microphone channel Hi. And so the received signal delay tau ij is actually the channel delay. And what if we want to align them? We just need to convolve with each other's channel. This will give us the aligned signal. If we look at the convolved channel, the channel delay is actually negative tau ij. So we can come to a conclusion, align the signal equals to convolve with another microphone's channel, whose channel delay is negative tau ij. Next, let's see how to align the signal if we don't know the AOA theta 1. we first compute all the possible microphone delays for every AOA theta, and each delay can be think of a pair of channels whose channel delay is negative tau ij theta. And we can construct a channel bank h hat theta using these delays. Now, assume I have the received signals where the direct path is from theta 1. I don't know theta 1, so I mark it red. We just need to convolve it with the channel bank. If the channel is wrong, say I try 120 degrees, the signals will not be aligned. If and only if we try the correct angle, 45 degrees here, I will get the signal aligned, so I know, oh, theta 1 is 45. This is how we align the received signal using channel bank. And how can we use this channel bank to model the echo AOA theta 2? We get the residual from the align and cancel, and this residual has no direct path. The next step is very critical. We delay and cancel our full channel bank using theta 1 channel we just get, as shown on this figure, to get the residual channel bank. Next, we take the residual Yij as the input together with another residual pair, another residual Ym. We try to align them using this updated channel bank H hat Ij and another H hat Mn. Only if I find the correct theta 2 will these two residuals be aligned and cancel. And following this procedure, we can find the AOA of the kth path, theta k, as long as we updated the channel banks modeling this residual. For more details and concrete proof, please refer to our paper. Let's see the results for the proposed IAOA algorithm. We first carry a simulation in a 5 by 5 meter room, and there is one speaker speaking to a 6 microphone array from a meter away. The signal will be reflected by the wall, and the heat map here plot the median AOA estimation error. For example, this red dot means that the microphone array is placed at coordinate 2, 2, and the speaker is placed at 12 different places that is 1 meter away. We can see that none of these estimation errors exceeds 10 degrees, showing that IAOA can accurately estimate AOA up to 3 paths. We also carry a real-world experiment by placing a Raspberry Pi at the corner of a bedroom. The Raspberry Pi is equipped with 6 microphones and placed 50 centimeters from the wall, and the speaker is placed at 6 different places from 1 meter away. This is the CDF of theta 3 error. We can find that the 80 percentile is less than 10 degree error. To sum up, we developed an algorithm to estimate the AOA of each echo, and the insight is that we can use align and cancel to cancel the already estimated paths. With a 6 microphone array, we can accurately estimate up to 3 paths. And lastly, IAOA works on any source. These 3 paths can be uncorrelated or echoes of another path. This concludes my talk, and thanks for listening.